Hi, my name is Hunter Addis, and this is for Engineering 1331, Krishna Koda, Tuesday, Thursdays, 2:30 to 4. This is problem number 1 of project problem number 1, which is numerical analysis. So the first part of the code is the housekeeping commands, and then down here we input the matrix and size the matrix, and then we check to see if the matrix inputted is an n by n plus 1 matrix, and if it's not, it's going to ask you to input another matrix. And then here is the part of the code where we put the matrix into upper triangular form, and then later down here is where you do the back substitution to find the x values for each column of the matrix. And then you output the new matrix and show the values for the x values. So what we're going to do is we're going to run the code for several different matrices. First one is a 2 by 3, which is an n by n plus 1. And as you can see, it puts it in upper triangular form. It also gives the value for the first column, x value, and the second column, x value. We can go back and run the matrix, or run the code again with a different matrix this time, which is a 3 by 4, giving us another n by n plus 1 matrix. And as you can see, it puts it in upper triangular form. All of the values below the diagonal are 0, and then it gives you the value for the first column x value, the second column x value, and the third column x value. If we run it one more time with a different matrix, we will see that again it gives us the right upper triangular form for the new matrix, and then the values for the x values for each column. Moving on to problem number 2. First off is the housekeeping commands. Then we create a loop that is able to rerun the whole problem. So this is a while loop, is going to cover the entire problem. And then you input the vector of coefficients, the first bound and the second bound. And then you check to see if those bounds are both positive or negative, and if the y values of those bounds are both positive, then you need to enter new bounds, and if the y values are both negative, you need to enter a set of new bounds. Then you can calculate the acceptable error, the y2, and plot the values of the error and the number of takes that the code runs, which is the number of iterations. And then in this loop, you're also looking at the acceptable error. So depending on the amount of error that you allow in your code, it will run as many times to get below that acceptable error. And then down here is where we polyfitted for the graph of the error and number of iterations graph. And then this is where we plotted the points, and this is an exponential polyfit to the same graph. So what we're going to do is we're going to run this code, and what I need is the inputs for that. So it's 3, 14, 26, and 1. So if we run the code, we can enter 3, 14, 26, and 1. The upper bound, or bound 1, is going to be -1. Bound 2 is going to be 1. And the maximum acceptable error is going to be 0.001. Again, you can see It'll ask the code if it wants to run again. Now I'm going to say no. These are the two graphs that it gives me. It gives me the number of iterations versus the error for each point, and then it will also produce the number of iterations versus the root for each point. And then, as you can see, this is based off the problem on the worksheet. The root comes out to be negative 0.04003906, which is the exact root that was on the test case. The max error ended up being below 0.001, which is why it stopped at this specific number of iterations, because the error was below the maximum allowable error, and the number of iterations, or the number of times the code had to run to reach an error below the maximum error, was 11 times. Thank you for watching my video. I hope you enjoyed it. Goodbye.